They've taken us on one of the great journeys of exploration.
Oh my God!
An expedition to Mars. Places never before seen by human eyes.
There's something just absolutely magical about that. It is like being there.
The rover's Spirit and Opportunity were expected to last just 3 months. More than 7 years later, Opportunity is still rolling. But Spirit has reached the end of the road.
We're driving a wounded vehicle through very treacherous terrain, and we knew it.
After a desperate effort to save Spirit, a fond farewell to a great explorer.
Good afternoon and welcome. I am John Callis, the project manager for the Mars Exploration Rover Spirit and Opportunity. The video you just saw is from a recent opening of a fantastic new documentary by the National Geographic Channel about the epic adventure of Spirit. We are here today celebrating this great triumph of exploration, this incredible mission of this Mars rover. As bittersweet as it is, at the conclusion of its time on Mars, we are here because we did what we said we would do. That is, leave behind no unutilized capability on the surface of Mars to wear these rovers out. And for Spirit, we have done just that. What is truly remarkable is how durable and capable Spirit really was on the surface of Mars. These rovers were designed for 90 days of operation, 1 kilometer of surface distance, and on her last day, Spirit operated for 2,210 Martian days and traveled over 7,730 meters and returned over 124,000 images. But it's not how long the rover lasted or how far she had driven, but how much exploration and scientific discovery the rover actually accomplished. Spirit escaped from the plains of Gooseup Crater, mountaineered up the Columbia Hills, survived 3 cold, dark winters and 2 rover-killing dust storms, and overcome debilitating malfunctions of equipment. But it's out of this adversity that the rover made some of the most striking discoveries on the surface of the red planet. And this has forever changed our understanding of Mars. It is this great adventure that we celebrate today. So at this time, I would like to invite the laboratory director, Dr. Charles Alachi, to come up and speak.
Thank you, John. 7.5 years ago, I tell you, it hit me really hard this morning when I got up and I said, gee, maybe I'd better wear that blue shirt that we all wore. You remember that? So I pulled it out from my drawer, tried to put it on. It was a little bit too tight. So I thought, well, maybe I gained some weight. 7.5 years is a long time. So it really, lots of changes happened in that time. Now, I'm going to do one thing. I would like to ask everybody who worked on Spirit or Opportunity to stand up. And I'd like everybody to thank them and give them a big hand. And by the way, the people who are working on Curiosity, your turn will come in about a year and a few months from now when we land successfully on Mars. Also, I want to acknowledge a couple of people who are not here and one person who are here who also played a key role. Orlando Figueroa was a program manager at NASA headquarters, or program exec. And Ferouz Naderi, who was a program manager here at JPL. They played both a key role. And Fook Lee, and your turn will be coming, Fook, in about a year from now. Now, I want to remind you only of one thing. Some of the people, particularly the people who were not here at that time or were not closely involved in it, it was a very tense time. not because it was only challenging. I mean, Ed here is kind of, giggling on it. But also NASA was going through a very tough time at that time. It was a lot of people who were saying, well, NASA cannot do, great things, or there was an accident, for the shuttle, which have happened. So it was really a very, very challenging time that we were facing when we were sitting on January 3rd, 4th, depending what part of the world you were in, sitting down waiting for seeing what's happening and getting that signal. And when you look at the videos, you can see it in the tense faces of Pete Theisinger, Richard Cook, all the people just before, as we were waiting for getting those signals. And I have to end it in one statement. Really, Spirit lifted the spirit of NASA when it really landed successfully. And that really created such excitement, and a new belief in NASA that NASA can achieve even things which are almost impossible. NASA can achieve that. But I have to say, even that we are complimenting Spirit a lot, Spirit was not an easygoing, rover. Some of you remember after, I guess, 1 week or 10 days, it got its memory overloaded or something. And for a while, we were really, really concerned. Ed and I remember getting up in the middle of the night, going and briefing, Sean O'Keefe, and getting on the phone with Sean O'Keefe as he was coming for opportunity. And we were, for a while, very, very concerned that is that a generic issue that is, before we understood exactly what it was. And here we had opportunity coming in, to do a landing. And there was a lot of concern on, do we have the same issue, on opportunities. But like, a young kid that you have, I have 2 grandkids, so I'm accustomed to them. Sometimes, they get a little bit testy, but then after they are all nice and you give them a big hug and everything is nice and dandy. And after 1 week, Spirit was doing great and really have accomplished, amazing things, since that time. So again, I want to thank all the people who have been involved in this amazing adventure that we have. And we have learned a lot from it, and we're applying a lot of that knowledge to the next step in our exploration of Mars, which will be happening a year from now, roughly, when we do that landing. And now I have the pleasure to introduce Dr. Ed Weiler, the Associate Administrator for Science at NASA headquarters, who was sitting next to me during that landing, and that excitement on that important day. Ed.
The good news is I don't have a prepared speech that I'll read because I was told I was going to speak as I walked in the door today. So when in doubt, I'll just tell the truth. And what I'll do is give you a little history from my perspective. I've been at NASA 33 years. At age 13, I decided I wanted to be an astronomer and work for NASA some time, and I did. And when I retire someday, I'll have 3 things that I'll remember, hopefully 4 when Curiosity lands successfully. But the 3 things I'm most proud of, because I was involved with from day 1 through fruition, was, of course, Hubble and all the repair missions, and then Spirit and Opportunity. Especially Spirit and Opportunity. Well, also Hubble, because they went from disaster to success. And that might surprise you. What do I mean from disaster? What does disaster have to do with Spirit and Opportunity? Well, let me tell you how we got those started. There was a thing, in a galaxy far, far away, there was once a Mars program, which had 2 missions called Mars 98, then a couple missions in 2001, and then a sample return mission starting in 2003. And that sample return mission had all of $500 million budgeted for it. You may know where I'm going here. I became the associate administrator when Wes Huntress decided to leave 2 months before the launch of Mars 98. So I was fully and totally responsible for those 2 missions. And of course, we know what happened. A day after the second MPL failed to land, Dan Golden, who was the administrator at the time, called me up, as he often did in the evening. I was at my son's, I'll never forget it, at some high school at my son's basketball practice. He was a little kid in those days. So I went outside to get better reception. It was a cold Annapolis night, and I was freezing on the cell phone, and Dan said, "Okay, you've got 24 hours. What are you going to do to fix the Mars program?" For those of you who knew Dan, you know of what I speak. And I said, "Dan, let me get back to you tomorrow." So overnight, I made one decision. I said, it doesn't take a rocket scientist to figure out we've got a flawed program. And Dan, what we should do is start from scratch. We should immediately cancel the 2001 lander because it was identical to the 1998 lander that failed. And we should get a new clean sheet of paper, get some scientists together, work with JPL, and plan out a new Mars architecture with a common theme. To make a long story short, Scott Hubbard came into headquarters, led a team of scientists, and came up with the theme of Follow the Water. We decided to do the 2001 orbiter because we hoped we could still orbit Mars successfully. Canceled the 2001 lander, canceled all the sample return stuff, and laid out a new architecture. And enough to see Dan Golden. There are only 3 people on Earth that know this story is true, but Scott Hubbard will testify to its truthfulness. And that was the day that we took the second mission in that architecture, the Mars Rover. I forget what it was called in those days. But we were going to propose to Dan going back to what we knew how to do, airbags. We had landed Pathfinder successfully with airbags. We tried to land on legs with the 1998 Mars Polar Lander. Why don't we go back to airbags? JPL had come up with a concept 3 years from launch. So we took Dan some view graphs using airbags. And he looked at it. And Dan was a very different kind of leader. He made decisions. He really made, if only some, well, I won't go there. That's right there. No, I'm not talking about NASA leaders. I'm talking about Washington. I won't get started. Anyway, Dan made a decision. He said, I like this. I think that's a good idea, but I don't like it. We're putting too many eggs in this basket. I want to reduce the risk, but we're using airbags, Dan. We know how to land on airbags. He said, no, I want you to do 2. And of course, Scott and I hardly had the budget for 1. We said, well, Dan, we're not even sure, we're still in view graph stage. We're not sure JPL could do 2. So we called up somebody at JPL, I forget who, maybe it was you, Charles, and said, you got 24 hours, can we do 2? Literally, this is a true story. And the next day we went to Dan saying, JPL thinks they can do it. Of course, we'll need more money. And Dan said, don't worry. And for the first time in like 20 years, the science mission director actually got money from other directorates at headquarters to help pay for that second rover. So that's a true story. So if you wonder why we have 2 rovers, give credit to Dan Golden. The reason Opportunity is still running today on Mars is because of one person on this Earth, Dan Golden. So the rest is, of course, history. I'm proud to say that architecture has led to 5 successes in a row now. Oh, Mars Scouts was created, too, at that time. And we actually did wind up launching that 2001 lander after a lot of changes, I might add, and it was successful. So we laid out that architecture, and we've had 5 successes in a row, hopefully soon to be 6, right, Pete? And I'll end with one other vignette, which is an absolute true story. I wish Orlando was here because Orlando deserves a lot of credit. Orlando was a hands-on headquarters type manager. He was at JPL an awful lot. I can't tell you how many times I called Orlando in my office at 8 o'clock in the morning after hearing the latest overrun on the 2 rovers, saying, Orlando, we got to kill one of the rovers. You got till tomorrow to convince me not to. So I threatened him with canceling the second rover. I lost count. And the last time I did this was about 12 months before launch, and I'll remember he said, give me 1 day to convince you. And I guess not only does Dan Golden deserve credit for that second rover, Orlando deserves some credit for that second rover too, because he convinced me not to cancel it during one of the overrun periods or whatever. So it's been a hell of a ride. Next to the birth of my 2 children, watching those rovers land successfully is a moment I'll never forget. Especially the second one, which was the secondary. Oh, I got to tell this story. Steve will appreciate this. 1 more minute. The science teams got together and said, where are we going to land? We've got to land in Gustav. That's the high priority. That's where the real science is going to be. So we said, yes, scientists will agree with that. And of course, Meridiani, that's a safe site. That'll be our second site. And of course, the rest is history. Gustav, there was some good science. Anyway, but when Opportunity landed, and Steve was standing next to me, I remember this. The first picture, of course, if you remember Mars 98 MPL, we waited 3 days. We kept telling the press, just wait a couple more hours, we'll have contact, and of course it never came. So we had really briefed the press really well. The concept of the death planet was born, 7 minutes from hell was born, all true. But we never, ever in a million years thought would land on Mars, and within seconds or minutes would get pictures back from Mars. And so the first picture came back from Opportunity. And, you know, I've been in the Colorado River Valley and seen the striations. The first damn picture said, my God, it's the Colorado River Valley. You know, there's water there. There was water there. Anyway, so this should be a positive day. It's not the end of Spirit. We still got a mission called Opportunity. We've got Curiosity. And most importantly, stick together. Don't let all the negativity about budgets and, you know, is Mars in, is Mars out. This nation cannot afford not to continue the Mars program, especially with our president saying that the ultimate destination for human spaceflight is Mars. We're the ones that are going to draw the maps and prepare the groundwork for those humans to get there. We have to continue the Mars program. It's not for JPL, it's not for SMD, it's not for NASA, it's for our country. Thank you.
Thank you very much, Dr. Weiler. With the rovers originally designed for only a limited stay in the relatively comfortable environment of the Martian summer, the many years of extended operations meant that these vehicles operate most of their time in a very extreme environment of frigid temperatures and dark skies, well outside their original design limits. The longevity and productivity of these rovers under such severe environmental conditions is a testament to the talent and dedication to all the people who design, built, tested, and operate these rovers. To remind us of the many challenges of getting safely to the surface of Mars, let's recollect with this video.
They've taken us on one of the great journeys of exploration.
Oh my God.
Liftoff of the Delta II rocket carrying the Spirit from Earth to planet Mars.
The rover has landed base pedal down, which means right side up.
Okay, as the attendants in this audience attest, there were hundreds of people involved in the designing, building, and operating of these vehicles. I would just like to take the opportunity to acknowledge just a couple of more. My predecessor, Jim Erickson, and the original flight system manager, Richard Cook. If we could acknowledge them, please. Now, it is my great privilege to not only recognize but introduce the person who was the manager of the Mars exploration rovers from their inception to their safe landing on the surface of Mars, Pete Tysinger.
Thank you very much. Actually, I think, John, it was about 4,000 people that worked on the rovers. But, I wanted to brought some people here to share some reminiscences of the period of time before the rovers actually got to the surface of Mars. Some of the challenges that were associated with those things, and some of the stories in a very limited amount of time. One of the most noticeable things about the rovers, when you see them, I think, for the first time, as they were eventually done, is the strange shape that the rovers have. This kind of fly-like, bug-like shape that the rovers have because of the solar arrays that we put on the rovers. And so I'm going to ask Kobe Boykins to my left to talk about how that came to be and why the solar arrays ended up that way and what the challenges were associated with their development. Kobe?
Okay, well, my name is Kobe Boykins, and I served as the solar array mechanisms and structures cognizant engineer for the rover during the development phase of both Spirit and Opportunity. And for those that don't know, I like to tell stories, so I'll try to go quick and I'll talk fast. But this was a half-time job for 6 months.
Go quick, talk slow.
Okay. It was a half-time job for 6 months. That's how it was sold to me when I first came onto this program. And it was 3 days before Project PDR when I first started. And there was a very sketchy configuration for what the rover solar array looked like. So I went into the PDR with a picture that said, I'm Kobe Boykins. This is a rover. I have no idea what I'm supposed to do. And it's supposed to make 950 watt hours of energy or something like that. And I started talking to Don Bickler, one of my mentors here, and he said, you got to figure out shadowing. You got to figure out how to do the shadowing. So we started cutting out pieces of paper, trying to figure out how the whole vehicle was going to work and the shadowing was going to work. And you got to remember this thing folded into a tetrahedron. So I was limited on the inside by the canister that held the parachute and limited on the outside by the lander. So there was very limited space to put the solar array. And then our illustrious PI, Steve Squires over there, right after I got named to this job, was in my office saying, can you get just another couple cells? I didn't even know what a cell was at that point. So we worked really hard, and what ended up happening is we sent a whole bunch of different configurations to the team, and they were talking about this last night during the wake, and these different configurations about how the vehicle would look, and I think somebody actually looked at it and said, oh, that one looks great, we should do that. And so I was like, oh, that was not the one I would have picked. And so we ended up with this sort of fold-out craziness for these secondary panels. So we had the primary panels and these secondary panels, and we were trying to figure out how they all went together in this really, really confined space. And ultimately, we ended up with something that worked, that we got enough cells on that made, quite a bit of power. We actually got the extra 10% that Steve was asking me for, and even ended up putting some outreach stuff on the back panel, on the -X panel for everybody. And that, for those that didn't know, on the back side of the panels is the little signature chip as well. So we actually ended up adding a lot of things to the solar arrays at the very end. But the little panel in the middle, what I call the gerrymander panel, if anybody's ever looked at the solar arrays from the top, the fold-out panels were the easy one, but that panel that's in the middle, that actually only makes like 10 watts. It's not really worth it. But the gerrymander panel was actually probably the most fun because it actually looks sort of like an elephant if you hold it on the side. So it was a lot of fun doing that design work and a lot of fun working with this team.
If you ever have read Steve's book, he talks about the discussion with the panels because around the time of the CDR, which would have been early in 2001, the project was looking for mass, and we were looking for very small amounts of mass, a couple of kilograms, because we were in the hole. And the winglets, the little parts of the solar array that fold out, were on our list, along with the things that the rovers roll out on. And Steve tells a good story in his book where he came to JPL to the meeting that was chaired by me to decide what to do, and he looked around the room and he knew it was 12-1, and he was not on the right side of this. And so we decided to take the winglets off, and which was going to cut his panel power by quite a bit, but would give us the 90 days according to our analysis. And then Kobe and his contractor cohorts came back with a new power analysis that indicated that with the winglets off, we were really in trouble. And Steve was depressed for about 20 seconds before he realized that means they're going to have to put the winglets back on. Later in the MER development, we began to worry about winds. The rover was heavier. I mean, we were heavier than Pathfinder, and so we had more issues with the airbags. we were worried more about the three-body problem and the swinging of the rover and the back shell with these large rad rockets that we're going to fire just above the surface. And so it occurred to us that maybe we ought to think about a way to try and cancel the winds out. And so dimes became developed, and Jeff Maelstrom was in charge of that development effort, and I'd like him to talk about that for a little bit.
I'm Jeff Maelstrom. I led the DIMES development. DIMES, it's the Descent Image Motion Estimation System, and as Pete said, it was a late addition to MER. You know, if you look in the PDR charts, you won't find it there. You look in the CDR charts, you won't find it there. It was really late 2001 when people started recognizing some of the risks associated with sustained winds. And they already had, the system already had tiers. Well, I'm going to back up. You know, when you recognize a risk late, your option space for solving it is really limited. And the only solution that was feasible was a machine vision-based motion estimation system, DIMES, in concert with the tiers RAD system, which was already on the back shell for providing control authority to compensate for horizontal velocities. And so in January of 2002, Pete made the decision that we're going to go ahead with this. We're going to implement DIMES. It was a new technology. The Mars Technology Program had been funding it, and you know, a team of folks worked to put this whole system together. But the core technology started with Andrew Johnson and Yang Cheng and the Machine Vision Group. They'd been funded by the Mars Technology Program, and now is our first chance to implement it in a flight system. Pete decided to accept the implementation risk to minimize the mission risk. And he managed that implementation risk, kept a tight rein on how we did it, but gave us a lot of freedom. He put he put in place 4 review gates, 4 gates by which he could measure our progress and our impact on the main implementation. This was supposed to be a risk reduction. We weren't supposed to increase the risk on the implementation team. Gentry Lee reviewed us every 3 months, and a group of people that Gentry put together reviewed us every 3 months. We had to develop the system to fit within the existing constraints of MER. Those constraints are, you know, this is a real-time control system, so it was time-related. We had to complete our tasks on a certain amount of time and within a certain amount of CPU budget. We had, in the final design, we started taking images at 2,000 meters. We took 3 images. That gave us 2 pairs of images. We tracked 2 features in each image, estimating the velocity between those images, and we had 17 seconds to do all of the image processing and computations in order to have the result available for the tiers RAD system. You know, we had to fit within the constraints, and then we had to verify that this system worked robustly in the conditions that we were going to face. We couldn't do an end-to-end. This is like any EDL system. You couldn't do an end-to-end system test. We had to put together a verification approach that was comprised of high-fidelity models, field tests. We spent a lot of 2002 out in the field testing with real hardware over Mars analog terrain in the Mojave Desert, and then test on the flight system itself, verifying all the timing, verifying the functionality of the software, verifying the phasing of all of our sensors. In the end, it all worked well for both Spirit and Opportunity. For Spirit, it was an insurance policy that paid off. If DIMES had not been available for Spirit, the landing velocity, the horizontal velocity, would have been at the limit of the landing system capability. So it was a good decision on Pete's part to incorporate this system, and it was a great opportunity for me and the whole DIMES team to work on Spirit and Opportunity. So.
You can imagine the pleasure of the management here and Ed when we were over budget and behind schedule, and we came up with this new idea that we're going to put on the rover. There was a lot of joy in that decision. The other thing that was interesting was remember the mass attempt, the mass removal that we had taken the solar arrays off and put them back on. Well, one of the little things we did take off was a Sunfind camera. And so it turned out that 4 dimes, this camera-based system, we had sitting in the rover, because we never bothered to take out the electronics, a camera interface that was just sitting there ready to use. Didn't have to get in and change any of the circuitry, just needed a cable, and we were home free. I was really surprised how well the vision software worked. That was the part I thought would be the Achilles heel of this. And it turned out that, camera calibrations and dust issues and all those things were a lot bigger worry. The machine vision stuff worked first rate. Spirit was the first of the rovers to be integrated. If you look at the ATLO schedule, the Assembly, Test, and Launch Operations schedule, we started putting Spirit together first, I think, and it was the problem child of the development. It was like your firstborn. It was always in the cookie jar first. It would drop things on the floor, and it was the one where the procedures were tried out and found to be wanting and had to be repaired before opportunity came along. So Kobe was also on the ATLO floor. In fact, you've probably seen pictures of him staring intently at the first rover drive with his nose just about as close to the floor as he can get, looking at clearances. And I asked him to relate a couple incidents out of ATLO that are Spirit unique.
So I actually got to serve, as Pete said, as part of the ATLO team, which was a great team to be on to actually build these 2 vehicles. And that they both had their own characteristics. And Spirit, as he said, was sort of the bad sister. And not just because the things that happened in landing, even before. And I was trying to think of a couple stories to relate. And that there's a couple that come to mind. And the first one is that we were sitting at the Cape and we were ready to go. Spirit was packed up and almost ready to go. And this is before we had the single point ground issue. And if anybody knows me, they know that I'm sort of the culprit for the single point ground issue, because it was the solar arrays that you had to fire the pyros for that caused that problem. And so we're sitting there, we're all stowed up, and we have everything locked up, and we're going through some of the paperwork. And I found in the paperwork a weakness. I'm not going to say it was an anomaly, but it was a weakness, and we thought, well, we better go check. And I don't even know if you know this story.
Probably not.
So I run down to the floor, and I talked to Matt and I said, we need to check this out. And Paul said, yeah, go ahead. And me, Chris, and Peter, and all the ATLO team went in, and we got this long wrench to go in, and we were going to check on the pan cam mass assembly because there was a fastener that didn't look like it was hard to tell if it got torqued or not. So we put the wrench in there. And it goes all the way in, and we find the technician that's doing it finds the right thing in the socket head cap screw, and he puts it in, and he says, Kobe, it doesn't feel right. And I'm like, okay, we'll pull everything out. And he pulls everything out, and out comes the screw.
Doesn't sound like it was torqued right.
So this was just the beginning of Spirit's fun. So that, we figured out a way to torque everything up, and we were going to actually do that. And then we had to open up everything because of the single point ground issue and having to go in and change out the card inside. So we actually had to fire the solar arrays again, and that caused the stress on everything, and then we got everything open. Once we got everything open, we're doing some work, and one of the people doing some work, and the connectors that we have are a pain, a big pain, and so we're working with the connectors, and there's little tiny washers. And on the ATLO floor, if you drop a washer, everything stops, and everybody starts looking for the washer. And so the lady that we all love, Mary Reeves, was working on this, and she dropped a washer, and everybody stops, and we all start looking for this washer. Now, you got to remember the lander pedals are open, and so the airbags are there, and they're like a big catch for everything. And so we're thinking, oh my goodness, we really don't want to take off the airbags because that's just a pain, and that's another 2 weeks, and we don't want to call Pete and say that we're going to be 2 weeks later with Spirit, and that would have moved opportunity in front, and it was all this craziness. So we're looking for this washer, and we haven't found it, and it's about 2.5 hours, maybe 3 hours of looking. And Mary says, well, what if I just drop some more washers, and we'll find out where they go? and literally, we're all running after Mary, like, no! And lo and behold, she dropped those 5 washers. We found 6. And so we found the washer that we lost. There you go. And so then we buckled up Spirit. We got ready to go. So, and I think one of the other things that was, I'm supposed to always tell 2 stories, but I'll tell one more. And that's the other big thing about MER, and at least Spirit, and if you can, I'm going to grab this shirt. This is one of the coolest things, at least for me, is that when I got down there, we learned that we launched using the Air Force, and these guys make these cool shirts. And a lot of you guys have seen these, and a lot of people purchased them, but I wanted to pull out the Murray shirt and just show, it's like the coolest thing, seeing Marvin the Martian on a shirt that's, associated with our vehicle Spirit. So those are the cool things. Thank you.
Getting the lander to the surface was the first part of the puzzle. We also had to get the rover off the lander and get 6 wheels on the ground in order to do science. Dan Limonati was involved in what we called impact egress on Spirit, and I asked him to talk about the challenges associated with that.
Hi, so I'm Daniel Limonati. As Pete said, I was one of the handful of engineers that was responsible for pulling off impact egress. And so our special joy on this mission was taking Kobe's creation and the mobility team's creation, right? Those poor guys had to stuff this rover, really 10 pounds of stuff into a 5-pound bag. And we had to figure out how to unravel it all on Mars. And so basically, impact egress, deals with the last foot of landing. And nobody, I think, when Weiler and company approved this mission, would have thought that the last foot, 40 centimeters of landing would take on the order of 10 to 12 days to accomplish on Mars, right? Because we didn't consider it landed until the wheels were actually on the ground. And so impact egress basically covers when we stopped rolling the rover, retracted the airbags, opened the lander pedals, deployed the solar arrays, Kobe's arrays, get to a power safe state. That took us a few hours. And then the PanCam mass assembly deployed, took some pictures, and on the morning of Sol 2, we had a Odyssey UHF pass and got about 20 megabits of pictures down. And while Steve and everybody else were jumping for joy on all the cool things that we're seeing and just happy to be alive, of course, the impact egress team is looking at that going, wait a second, there's an airbag that didn't quite go where it's supposed to go. And so we're sitting here, kind of biting our nails a little bit, but we had contingency plans for that. And so the egress team started working contingency plans. And the next step in the process was basically standing up the vehicle. And so I kind of think of this as, there's lots of analogies. I think of it as Harry Houdini in a box. And Houdini was in the box for 8 months. He's a little stiff, right? And so now you got to slowly undo the mobility system. And that process took about 2 days on the surface of Mars, 2 sols, with 4 go, no-go decisions. One of the interesting highlights from Spirit was, she was the first one on Mars. And so even though we'd spent 2.5 years designing and testing all of this, the signature that we were looking for when we were standing up was missing something on that second day. And we're looking at the data going, gee, I don't know if the latch is all locked in place. And so being responsible for that part of the mission, the stand-up in particular, I didn't want to tell the mobility guys, hey, don't drive too hard because the suspension system might collapse on you, right? That would not be a good position to be in. And so after deliberating for a night and thinking about it, we came back and basically redid that move, confirmed the system was in place, and moved on. By then, the egress team had gotten through their part of figuring out how to deal with the airbag. And we spent a couple days kind of dancing around on the lander to avoid the front egress path that was blocked, turned around, drove off the other side on Sol 12. To everybody's joy and jubilation, of course, the impact egress team then, like everybody else, collapsed for 2 days to come back and to get ready to do this again. So anyway, that's kind of 2.5 years and 3 minutes.
I think that there's a good role model here for us as we continue working at stuff that JPL does. Okay, you've got to remember the environment. We've just landed this event. The press is camping out on the mall. We're going in front of them every day to talk about events. Dan's nervous that the damn thing stood up or not, excuse the language, okay, and comes in a little nervously to the project office and says, I really think we ought to, squat back down and stand up again and see if we can get them latched. Okay, and I think he deserves, and the team deserved a ton of credit for, being brave enough to come and say, I think, guys, we ought to stop and think this thing through and do it right and make sure we're right. And I think we need to always take that lesson when we're under schedule pressure and when we're being driven by events. And so as Dan said, we drove off the lander and saw Steve's beautiful picture in the rear has cams of the lander. They're going to kick me off the stage, and us. There's a lot we didn't talk about. We didn't talk about the impact of the short schedule on the team and on everybody's nerves. We didn't talk about the parachute issues. About a year before launch, we didn't have a working parachute because we had an inflation issue with it. We didn't really talk very much about the blown ground fuse and the meetings we had with Ed and Charles in the last few days before launch to convince them that we really were safe to go, and to commit this $800 million, one half of the $800 million vehicle into the void. We didn't talk about issues during the cruise. We had four anomalies during cruise, design issues that we had to repair. We had the great-grandmother of all solar storms there, and so cruise was kind of cut in half, because I told Jim that for half, when the red side of the sun was pointed to us, he couldn't do anything with the vehicle that he was supposed to be getting ready for surface operations. And we didn't talk about the dust storm at Mars and the changes we had to make to EDL and the parachute deploy, or the Sol 18 anomaly that was what Ed referred to. It was a very challenging adventure, and I think part of its appeal is how the drama played out. A very short schedule, a very committed team, a very successful project, the traumatic landing events, the Sol 18 anomaly, the recovery just before our opportunity got there, and then 7 years later, here we are, and we've still got one working. So it's been a fantastic trip so far.
Thank you very much, Pete, and thank you others for those wonderful, exciting remarks. Spirit's discoveries have changed our understanding of the red planet. We know now that Mars was not always a cold, dry, and barren planet. That one time liquid water flowed on its surface, sustained by a thicker atmosphere and warmer temperatures. At least kilometer-scaled lakes persisted in places. And there were even sources of energy, hydrothermal systems, that could have supported life in this earlier habitable world. Let us review just a few of these moments of discovery with the following video. Well, now let's hear directly from some of those scientists about some of the great and significant discoveries on the surface. It is my very great pleasure to introduce and to acknowledge the principal investigator for the Mars exploration rovers, the ever-essential Dr. Steve Squires.
Thank you, John. The last panel did a terrific job of giving you a sense of what an adventure it was to get Spirit from that initial concept to the surface of Mars. 3.5 years of terror and tension. That 3.5-year adventure was then followed by another 6-year adventure of scientific discovery on the Martian surface. And what we're going to try to do in the next minutes here is share some of that scientific adventure with you. I'd like to start with the first picture. And the first picture that I have to show is my favorite Spirit picture. Of the 120,000 pictures that Spirit sent back, this is my absolute favorite. It came down, Pete helped me out, I think it was like Sol 25, something like that. It was about 25 days into the mission. You've heard people mention already a couple times the Sol 18 anomaly. 18 days into Spirit's mission, we appeared to have lost the vehicle. She just went silent. And we didn't know what was going on. It was absolutely terrifying. We were up, not sleeping for 3 days straight. It turns out Spirit was as well. And it was because of a software problem. The team did a brilliant job of analyzing what was going on, solving the problem, getting control of the vehicle. This was the first picture that came down after the anomaly, showing us that we had a healthy vehicle ready to start exploring on the surface of Mars. So if I could go to the next picture, this shows kind of the view that we had from our landing site. Now we went to Gusev Crater hoping to find layered sedimentary rocks laid down billions of years ago in a Martian lake. And when I saw this scene, I managed to convince myself for about 3 days that that's what a Martian dry lake bed should look like. But then we looked at the rocks, and the first day of Geology 101, the first thing they teach you is the difference between sedimentary and igneous rocks. Well, it turns out these were igneous rocks. And we quickly realized that every rock for miles in every direction was lava too, except maybe 2.5 kilometers off to the southeast, there was this beautiful range of hills that we named the Columbia Hills after the Columbia Space Shuttle. And after about 100 Martian days into our 90-day mission, we decided it was time to sprint, rover speed, to the Columbia Hills and see what we could find. Could I have the next one? So this is the view that we got when we first arrived there. On day 156 of our 90-day mission, we crossed over into the Columbia Hills and everything changed. The hill that we first got to was this one. We named it Husband Hill. It's named after Rick Husband, who was the commander of the Columbia when it went down. And this is the hill that we chose to climb. If I can have the next picture, what this shows is the route that Spirit followed over hundreds, something like 550 Martian days of mountaineering. First ever mountaineering on the surface of another planet, finally working our way to the very summit of a mountain as tall as the Statue of Liberty. And like any good mountaineer, when you get to the summit, you have to take a picture. So the final picture I have to show, the next one, shows the view from the summit of Husband Hill, taken about 600 days into the mission, looking to the south in what turned out to be, for Spirit, the geologic promised land. Opportunity was the lucky rover. Opportunity made most of her most critical discoveries in the first 60 days after we landed. Spirit's real mission of scientific discovery began when we headed down from the summit of Husband Hill into the terrain that you see in this picture here, after more than 2 years, 2 Earth years on the surface of Mars. So now I'm going to turn it over to 3 of my colleagues, starting with Odetta Harrison, to tell you about some of the discoveries that Spirit made as we headed down the hill.
Yeah, this is perfect. I'm going to try to pick it up right where Steve left off. But before I do, I just want to say that for me, this rover really has very much of a human aspect to it. This process of exploration, it has very much of a human aspect to it. I mean, there are a lot of people in this room that have contributed to designing it and building it and guiding it and interpreting the science results from it. But I think this rover really also affected us. I mean, both rovers do. I mean, I got my start being a student at Cornell of Steve's, where Steve was my role model, and Spirit was just a twinkle in his eye. So, so I think a lot has, I mean, in a lot of ways, these rovers have affected us. And many of the results I'm going to show you are actually from a study led by one of my students, one of Steve's academic grandsons, that published this. So, so if we can have the first slide, please. So this is a view actually looking up towards Husband Hill, from which Spirit climbed down. And one of the first things you see right in the center of the frame there is a feature called home plate. And anybody who knows baseball knows why this feature is named home plate. And this was the target of our investigation for several thousand sols, actually, on the surface of Mars. So we flew in over home plate, looking over on the, let's see, on the west side of home plate. And right near that west side, Spirit parked for a while, looking at the physical geology of home plate. And that's what I want to talk to you about. How did this thing form, and why does it matter? So if we can have the next time frame. This was one of our first views of the edge of home plate, which turned out to be a couple of meters high, about 80 meters across, elevated sedimentary deposit. And this was one of our first views. There's actually a lot of things to look at in this image. There's layered rock near the top. There's more coarsely layered rock near the bottom. And then near the very bottom was one of the most exciting things that actually one of our team members spotted from very far away, which I always thought this was absolutely amazing, that he could see this. And you could see right near the bottom of the frame is this rock that appears to have deformed the layers, the coarse layers near the bottom of home plate. So if we can have the next slide. This is this rock, and you can see that the rock seems to have deformed one of the layers. So we were pressed for an interpretation of everything I just told you about. A sequence of layers elevated above the topography, or they seem to have, sometimes they cross each other, sometimes they're just coarsely layered and parallel to each other. And then there's a rock that comes in and deforms one of these layers. And the interpretation that eventually I think came out and is fairly widely now accepted, is that this was a big volcanic eruption, a pyroclastic eruption that deposited these layers one on top of another. There are several possibilities. One possibility is that the eruption actually happened right at the center of home plate, and that the sediment just fell on top of the hole. And the other is actually that it happened somewhere else, and that the sediment just got captured in home plate. Either way, this was probably very violent eruption, which physical volcanologists refer to as pyroclastic eruption. And this rock is an example of a bomb sag. It's what happens when a piece of bigger rock actually lands in deformable layers of sediment, maybe even wet layers of sediment, and deforms it upon impact. So one of the things we did was actually very carefully look at the geometry of these layers in order to test whether this hypothesis is right or not. We looked at the geometry of these layers on this side of home plate, and it turns out that if you trace these layers very, very carefully, you notice that they're all dipping downwards. They all have a slope down towards the center of home plate. And if we could have the next slide, if we now pan around to the other side of home plate. In fact, Spirit did this, I remember, in this crazy march around home plate. You know, you have to imagine for yourself. I mean, about 700 days into this mission, she lost her front right wheel, right? So we're hobbling around trying to explore as much of home plate as we can on 5 wheels, not really sure what our mobility system can do. Some of our great RPs were sort of figuring this stuff out at the same time as the rover was actually operating on Mars. So we drove around to the other side of home plate and took a look at the layers there, imaging all the way through. And in fact, if I could have the next time step, we found more layers. These layers actually seem to be accumulating on top of each other. If you look very, very carefully, you can actually see where the beds fold over each other. This is a distinctive sign of rapidly aggrading pyroclastic eruptions, these eruptions that deposits the sediments very quickly. And these layers were also dipped down towards the center of home plate. So all of home plate had the structure of layers dipping down towards the middle of it. So if we could go to the next time step, this is just a cartoon showing how these layers cross each other. And if we go to the last time step, you see that those charts around the map of home plate show you the direction at which the slopes of the layers actually point. And each one of those plots in each position shows you that the layers are pointed towards the center of the same feature. So either the sediment, as I said in the beginning, draped a pre-existing hole in the ground, or else this was actually the source of this big eruption on Mars. So why does all this matter? I think there are many reasons why this matters. One is that pyroclastic physical volcanology is a field that really so far hasn't had many examples to be studied in situ only on Earth. And here is one example where we can really understand how this process happens on another planet. Another reason is that a pyroclastic eruption, a surge deposit, is one of the hypotheses for the formation of all the rocks that we see on the other side of the planet, on Opportunity. And I think it's very useful. In fact, it came up today in our team meeting. It's very useful to have one example of sort of the archetypical, just the symbol of pyroclastic eruption on Mars. And I can go on. There are connections to maybe the presence of water at home plate, and Steve will tell us a lot more about the composition of the Columbia Hills.
All right. Thanks, Oded. So I'm Steve Ruff. I'm the mini-TESS downlink lead, our infrared spectrometer, and my task on the mission was to help find interesting rocks and places to drive the rover to using this instrument. And we went to Gusev Crater in search of a lake, and what Oded didn't tell you about home plate is that it was our best last hope for evidence for lake sediments. And we were both excited but disappointed to discover that it was a story of interest to a volcanologist. My first slide shows, there we go. This is sort of a bird's eye view of our whole mission, from start out on the plains to home plate. You can see sort of at the bottom. And so we arrived there, discovered that it wasn't what we had hoped for. It wasn't lake sediments. Spent a winter parked beside home plate. And then finally on Sol 1100 of our 90 Sol mission, as we like to say, we went to about the furthest extreme that rover went, about almost over 2 miles from its landing place. We got on the trail of what turned out to be a very exciting discovery. So the next slide shows a very ratty little outcrop of rock, maybe 6 inches high and 18 inches wide or so. And this was our first clue that we were onto something interesting at home plate. So our mini-TESS instrument looked at this, and through very dirty, dusty mirrors, by this point in the mission that instrument was essentially contaminated by dust, but I could just make out the features spectrally of what looked like silica, and I'll explain what silica is and why you should care. So we got on the trail by Sol 1100. The next slide shows we moved over the next 2 months actually up to the edge of home plate, and there we encountered more of this sort of ratty looking outcrop that our infrared spectrometer said this looks like more of this silica rich material. Let's finally get our other instruments onto this outcrop, and we did. And so this was the first place that we deployed all of our instrument suite, and lo and behold, it was this high silica material, and we could tell from our spectra that it was this opaline silica. And again, I'll conclude with why you should care. So we were finding opal-rich rocks on Mars, opaline silica. Now this is a place covered in lava flows, and to find something high in silica is totally the opposite of what you'd expect in a very lava-rich place. So from this location, the next slide shows, that's the actual outcrop, very unusual eroded outcrop, rich in this opaline silica. So yes, we did confirm that this outcrop of this material was rich in silica. The next slide shows what ultimately culminated in one of the most famous pictures of our mission. There you can see this light-colored streak in the dirt, and this is where we turned lemons into lemonade with our broken wheel on that rover, which was dragging behind us, and it was exposing interesting material in the soil. And in this case, we exposed more, we had done this routinely even, more of this light tone material, and we all assumed it was the same stuff. But from this position, we looked over with that spectrometer, and it looked like more of this silica-rich material. And then we did drive the rover over to it, and lo and behold, it was the most pure, extreme example, over 90% of this SiO2, this opaline silica. So it was really the culminating feature. Now the next slide shows that famous picture from PanCam of this trench that we dragged inadvertently with a broken right front wheel, exposed this now clear indication of this story. So the next and final slide for me shows why you should care. So this opaline silica is a kind of mineral that forms in environments on Earth that are hydrothermal. So this is sort of one of the holy grails of Mars exploration, is finding places on Mars where warm or hot water is interacting with rock. And that's because on Earth, these are places where microbes like to live. Microbial life grows on the side of hot springs. It grows at the edge of fumarolic steam vents. And the beauty of opaline silica is it actually can entomb those same microbes. So this is a place on Mars that could have had life. It's a potentially habitable environment, and it could have even preserved that microbial life in this silica, entombed for us to maybe go back in the future and collect some of that. So the lake story sort of faded, but this new story of hydrothermal alteration and potential habitable environment came into Spirit's life and our lives, and Dick has more of that story. Go ahead.
Thanks a lot, Steve. I'm associated mostly with the Mossbauer team, and I'm interested in the weathering and alteration products on Mars. And if Steve is a volcanologist, I'm a credologist. We all know that from images that Mars has lots of what look to be like extinct river channels on it. And we all know from today that Mars has a very thin CO2 atmosphere. Well, one way to get these river channels is by having water running a long time ago on ancient Mars. And one way to do that is to have a warm Mars with a very thick CO2 atmosphere, so it rains a lot and form these channels. Now, when you have a lot of water and a lot of CO2, what happens is you get carbonate precipitation. And this idea has been around since the 80s. And it hasn't really been resolved at all, because there was a where's the beef issue here. We haven't detected any of this carbonate that should have been there if Mars was warm and wet and formed these carbonates. Well, Spirit had a lot to say about all this. Could I have the first slide, please? Spirit came up the top of Husband Hill, sped down the hill, and snuggled up to the outcrop on the right arrow there. This is the Comanche outcrop, and that whole area in there turned out to be carbonate rich, and I'll describe how we knew that discovered that in a minute. We came to this outcrop in 2005, and we published the paper about this in 2010. It took us 5 years to figure out what was going on here. And part of the reason was we had to do some homework. One thing that had to happen was the mini-test had to get the dust out of the data, which Steve worked on. We had to go back to the laboratory and look at some Mossbauer data. We knew that the outcrop was different, but we didn't, in 2005, but we didn't know why. Next slide, please. This shows, on the left is a plot of the Mossbauer spectrum of Comanche. And you can see some peaks there, and the yellow ones, we know from the position of the peaks that this is due to an iron-bearing carbonate. What we had to do is go back to the lab and take some laboratory spectra of this kind of material, and lo and behold, we identified this, at least from the Mossbauer point of view, as a carbonate-bearing mineral. But there are lots of different kind of carbonates, and we've got a wonderful suite of instruments on MER. And if we're going to call something a carbonate, everybody's got to play together. And the spectrum on the right is the mini-test spectrum with the dust taken out of it. And the arrows indicate positions which are indicative of the fundamental vibrations of carbonate. So now we have two primary instruments on the rover saying carbonate, carbonate. And another good thing about the mini-test is it was not only able to look at where the Mossbauer and also the APXS analyzed. It could look around at the other parts of the outcrop and confirm that it wasn't just this teeny weeny spot that had the carbonate, it was the whole area around. So there was a lot of carbonate there. And the mini-test data, the Mossbauer data, plus the APXS data, which provided the chemistry and the amount of carbonate that could be there, we put that all together and did the calculations, and there's between 16 and 34% carbonate there. That's a lot of carbonate. And time will tell whether this is the part of the warm, wet, early Mars. That's why we care about that. And so it's the instruments on MER really played together well here. And I should also point out that this whole voyage of discovery was so successful because not only the instruments played well together, but this whole MER team played well together. Okay. So with that, I'll pass the baton back to Steve.
All right, thank you, Dick. When you get to the end of something like Spirit's mission, you find yourself asking yourself questions about what's our legacy? What's the legacy of this mission going to be? I think it has a couple parts. One obviously is scientific. I mean, you've gotten a sense of that story here today. Mars today is a cold and dry and desolate world. But Spirit's discoveries have helped show us that in the past it was a very different place. At Gusev Crater in the Columbia Hills, it was hot. It was violent. There were explosions. There were steam vents. There were hot springs. There were ecological niches that would have been capable of supporting some of the hardy sorts of microorganisms that you can find in extreme environments on Earth today. So I think the scientific legacy, while it will continue to grow as we continue to analyze the data, is clear. But there's a human dimension to the legacy as well. This mission didn't turn out the way I expected it to. What was initially conceived as a fairly simple geologic experiment ultimately turned into humanity's first great expedition of exploration across the surface of another planet. That certainly wasn't what I expected, but that's what it's became. And when you think about the way the great historic voyages of exploration have typically played out in the past, the explorers would get in their ships and sail off over the horizon, and then 2 or 3 or 4 years later they'd come back, or they wouldn't, and the ones who came back had stories to tell. But we've been able to tell the story day by day, sol by sol, as it has unfolded, and to share that with literally everyone in the world who wanted to follow along. And we know that this story has captivated and has caught the imagination of many people. And I think that's important. These rovers were built in part by a team, I'm talking about the older people like me on the team, who grew up in the 60s and watching Mercury and Gemini and Apollo on television and dreaming of sending spaceships to Mars someday. And then we got to do that. And you know, my fondest hope for the legacy of Spirit, in addition to the scientific legacy, is that somewhere, maybe many somewheres, there are young people, kids, who watched the Spirit landing on television and saw us all jumping up and down like we just won the Super Bowl, and who heard about the scientific discoveries and the hot springs on Mars and all that kind of stuff, and looked at that and said to themselves, that's pretty cool, but I bet I could do even better. And if that's part of our legacy, I think that'd be one of the best things we could have accomplished. Thank you.
Well, we have an opportunity here to ask a couple of questions of the science team. We have 2 microphones that are positioned in the back of the room. So if anyone's interested in asking a question, I'd invite them to come up. We have time for just a couple. But while you're thinking about the question and making your way to the microphone, maybe I'll ask a question of the team right now. Steve, is there any instrument that was available at the time we were building these rovers that you wish you could have put on the rover and carried with you to the surface?
Okay, are you going to give me more time and more money? No, seriously, if you're going to give me more time and more money, I can give you a long list of things I would have liked to have flown. If we have to stick with the budget and the schedule we had, I wouldn't change a single wire or a single screw. I wouldn't dare. It's worked out so much better than I anticipated. But if you said, what are the kind of instruments you'd really like to fly, a lot of them are the kind they're going to fly to Mars on the Curiosity rover, coming very soon.
Mm-hmm. Okay, let's see. Do we have anyone who wants to offer a question? Yes, please. Use the microphone.
I'm confused about the timing and what happened on the initial landing of Spirit. Dr. Weller said something about the first week, and Dr. Squire said something about 18 days. Were there two separate?
No, it was one event, and it was the 18th day of the mission. It was Sol 18 when we nearly lost the vehicle. We didn't actually get off. I think what Dr. Weiler may have been referring to was that event took place 1 week after we had driven off of the lander and onto the soil. So we did the egress that Daniel Limonati described off the rover on Sol 18 or on Sol 12, and then Sol 18 was when we lost contact with the vehicle.
Okay, and it was software which was fixed.
It was software, and it took a brilliant piece of insightful detective work by the team to figure out what was going on. You got to realize that when you have a problem with a spacecraft 100 million kilometers away, the thing that you use to troubleshoot the problem is data in the telemetry stream. All we had to go on was that there was no telemetry stream. And that made it very difficult. Then we started to get little snippets, little pieces, tiny bits of data, and people on the team who were deeply familiar with the software because they designed it and built it were able to intuit out what was going on, figure out what had happened, and send up some commands that allowed Spirit to regain her sanity and to survive.
Follow up, how long does it take for commands to get, from JPL here to, they go straight to Spirit Opportunity?
Yeah, the commands go straight in, and how long it takes the commands to get there depends on where Earth and Mars are in their orbit. When Earth and Mars are as close together as they can be, it's about 3.5 minutes. When they're on opposite sides of the sun, it's about 20 minutes.
Okay. All right, well, let's take this opportunity to thank this extraordinary team one more time. Let me conclude. We can't do the impossible. We can't make these machines operate forever. But we have come as close to that as possible as humans can. Spirit's very accomplished exploration of Mars has rewritten the textbooks about the planet. Further, this rover has changed our understanding of ourselves and our place in our universe, and has approached the questions of, are we alone, and what is the future of this world? But beyond all the exploration and scientific discovery, Spirit has given us a great intangible. Mars is no longer this distant, alien, unknown world. It is now our neighborhood, and we go to work on Mars every day. But let's also remember this great accomplishment did not come at the expense of vanquishing some foe or outscoring some opponent. Spirit did this. We did this to explore, to discover, to learn for the benefit of all humankind. And in that respect, these rovers are the highest aspiration of our species. Well done, little rover. Sleep in peace, and congratulations to you all. Thank you all very much.